Okay, so we don't have a ton of time left today, but we can keep working on that one example problem. Before we go back into that, the second exam is coming up a week from Thursday. So exam 2, that is just going to cover rigid bodies and linkages. And so contained in this is moment of inertia, those angular quantities, but the only problems are going to be rigid bodies alone or else in linkages. So you have all the practice problems you need for rigid bodies. By Thursday, I will get a couple more linkage practice problems and solutions posted. But you also have the examples that we've done in class of linkages, so you should use those. So use the relevant practice problems. And example problems from class. The practice problems that I still have to give you for linkages are going to be along the same lines as those example problems. There's not going to be anything too new. Okay, and then for quiz questions, we didn't do quizzes for a while. There's a quiz posted for, when was it? Last Thursday? And so the quizzes, I guess the quizzes for Thursday, today, and this Thursday will be on the exam. But, there's not much there. Just make sure that, just make sure you know those questions because those are easy points to get, especially now that there's so few and they're painful points to lose when it's based on so little information. So Tuesday 3:13, Thursday 3:15. No, there wasn't one for Tuesday, right? Okay. Tuesday 3:20 and Thursday 3:22. Okay, so it's a pretty manageable amount of stuff, but in order to do that stuff to solve those linkage problems in a class when you're like a little nervous about the test or whatever, you're going to have to do some repetitions before the test. Okay, so if you do those, there's not a ton of like thinking about this stuff, but you just have to ingrain the methods, All right. Any questions about that? So last time, so continued. We were doing an example problem, a linkage that looked like this. Where this was all an equilateral triangle. All the lengths were 1 meter long. And the members each had a mass of 10 kilograms. And just so we were all on the same page, I put the coordinate system there, and I numbered them member 1 and member 2, and I called this joint A, B, and C. We already did member 1. The free body diagram looked like this. We had the weight, 98.1. We had the reaction force at that pin. And that's a force vector because that's a pin. And then, oh, and there was a force acting down here of 200 newtons. And that 200 Newton force acted on member 1 just because of our chosen convention. Okay, you could put that on either member, but you can only put it on one member, and you'll get the exact same answers for the external loads. Okay, and then we also had a force F12 applied to member 1 by member 2. And out of this, we only got one equation of motion. Why did we only get one? Right, exactly, because of the fixed point. So our first equation was negative 0.866 F12x plus 0.5 F12y minus 3.33 alpha 1 was equal to 124.525. Is that right? Okay. So there's our first equation. And the variables so far, we have F12, X and Y components, and we have alpha 1. So now we're moving on to the second member. Okay, so we have the weight still, 98.1. What type of force is acting at this end? At the ground. Yep, a vertical force because it has to be perpendicular to the ground because of the rollers. It's perpendicular to the direction that it's allowed to move. So we'll call that FB. That's just a single variable because we know the direction. And what do we have up at this pin? Right, it's, I'll write that as F21, but when we reduce variables due to Newton's third law, that's going to be negative F12. So before we go into this, let me ask, like, do you have intuition about how, yep. Oh, okay. So up here, we had 50 newtons. Okay. So how would these match up? Like, let's think about that for a second. So say that we used a different convention and this 200 Newton force was applied to member 2 here instead of member 1, or if we use the same convention and just numbered the members differently. Like it seems odd. Like is this force going to be the same? That F12, is that what's going to be the same? I think we can all agree that it's not too hard to imagine that FA and FB are going to stay the same no matter where we apply that force. Well, what would happen is the 200 Newton force in F12 act at the same point, okay? So there's a single force vector that acts at that point C, okay, on this body. And if you add up that total force, that will be the same no matter which one of these members you apply the 200 newtons to. So this F12 is going to be different, but the total force acting at that point on each member is going to be the same in either case, okay? If you ever have, you know, half an hour or something and you want to make sense out of that, just work this problem the other way. I mean, I think it's, you know, I sort of like doing the same problem over and over again, multiple ways. It can be a little boring, but I think it helps clear a lot of things up. And that's a good thing, I think, to understand how that works. Any questions about that? Okay. So here's the free body diagram. And so now professional aquanauts, that's not a vector. Yes, it is. Row for money. Okay, so we can still use that same origin. So let's start with this force F21. What are the coordinates of that point? Yep. And, oh, you know what? I'm getting a little ahead of myself on doing this calculation. I'm not following the order of the steps. Does this member have a fixed point? It doesn't, so we're going to have to do the about point as the center of mass, right? So A is the center of mass. And so the moment of inertia about the center of mass is 1/12 times the mass times the length squared, so 0.833. Okay, what are the coordinates of the center of mass? Yep. 0.433, 0. So subtract these and you get negative 0.25, positive 0.433. The force vector is F21x and y. And you get negative 0.25 F21y minus 0.433 F21x. Yeah. Yes. Okay, and now where gravity is applied, that acts at the center of mass. The about point is at the center of mass. Question? Okay. Subtract these two and you get zeros because gravity acts at the about point. So the force is 0 negative 98.10, no moment. And then we have the 50 Newton force. Where does that act? 100. The about point stays the same. So the row vector is 0.25, negative 0.4330. Say we're doing the 50 here, so negative 50, 0, 0. And so you get 0, 0, and negative 21.65. And then last is that reaction force, FB. That acts at the same point, 0, 1, 0, 0. About point stays the same. So the row vector is 0.25, negative 0.4330. The F vector is 0, FB 0. And so you get 0, 0, 0.25 FB. For this one, do we have to use Newton's second law? Yep. So Newton's second law says F21x, F21y plus 0, negative 98.1 plus negative 50, 0 plus 0 FB is equal to the mass times the acceleration vector. So A COM x, A COM y. And what do we know about, well, the acceleration of the center of mass? Forget that. So let's just leave it like this for now. And then rotational Newton's second law. The only components that matter are the y component, the z components. So we have negative 0.25 F21y minus 0.433 F21x minus 21.65 plus 0.25 FB is equal to the moment of inertia, 0.833, times the angular acceleration of body 2. So before we list these in our set of equations, our final set of equations, are there any of these variables we can reduce due to Newton's third law? Yeah, and if you see those earlier than now, you can put them in whenever you want. But so I'm going to write this as negative F12x minus 10 A COMX. And if you have more than one body that you're doing about the center of mass, then you need to number these. So center of mass of body 2, you know what I mean? Like, becomes sort of a bookkeeping issue. and that's equal to 50. Then the second one says negative f12y plus fb minus 10 times the acceleration of the center of mass y is equal to positive 98.1. And the last equation says positive point, I'm going to reorder these, 433 f12x plus 0.25 f12y plus 0.25 fb minus 0.833 alpha 2 is equal to 21.65. So these are equations. We only had one equation before this, so these are equations 2, 3, and 4. And for variables, we still have the ones that were from the first body. F12 vector and alpha 1. And now we also have FB, alpha 2, and the acceleration of the center of mass. So that's 1, 2, 3, 4, 5, 6, 7 variables. Okay? What's different about this than the example we did before this? Well, last time we had only 2 more variables than we had equations, and the only constraint equation that we could use was the constraint saying that that joint doesn't fly apart, okay? That the accelerations of that joint are the same according to this body as this body. Now we need one more equation. Do you have a sense physically what that other constraint is going to be? So we're still going to use that joint equation. But there's one more thing. If you look at, like, what else do we know about this structure, about its motion? We know that this roller is going to stay accelerating horizontally along the ground. Okay? So we know that the acceleration of this point B is going to have 0 y component. Okay? So the first constraint is going to be the acceleration at the pin joint is the same according to both members. That'll give us 2 more equations. And the second constraint is at the roller, you can't have any acceleration in the y direction. That'll give us 1 equation. And as long as we don't add any new variables in coming up with those 3 equations, then we'll be at 7 and 7. Okay. So first, let's work on the pin constraint equation. So according to member 1, we want to calculate the acceleration of that pin. What equations do we have to use for this? We know that we always have to use this one. The question is, do we also, in this case, have to use the relative motion equation? So this one we always have to use. This one we only have to use sometimes. When do we have to use it and when don't we? You have to use it if you're doing it about the center of mass. In this case, we're doing it, member 1 has a fixed point, so we're not going to need this. Okay, so the acceleration of that point C is equal to, the angular acceleration is 0, 0, alpha 1, crossed with that r vector. What's the r vector? That's the r vector is from your about point to the point that you're interested in. So in this case, it's C, the vector going to the point C from the pin at A. Okay, so that's going to be 0.5, 0.8660. And I think this was instantaneously at rest. Is that right? So this is no angular velocities. So this all goes away. And we get the acceleration of C is equal to negative 0.866 alpha 1, and then plus 0.5 alpha 1. Any questions about that? Okay, now according to member 2, you have a question? Okay. This is how I think. Ooh, pick me. Okay, so member 2, we're going to use both of those equations this time. So since A is the center of mass, we're going to have the acceleration of C relative to the origin is equal to the acceleration of C relative to the center of mass plus the acceleration of the center of mass relative to the origin. Okay. And we're going to use the rotation equation to give us that the acceleration of C relative to the center of mass is equal to alpha 2 crossed this, I'll call it R2, plus 0, because again, we don't have any angular velocity. Okay, so the acceleration of c relative to the center of mass is equal to 0, 0, alpha 2. And what's the vector going from the center of mass of body 2 to the point C? This is going to the point C, so the vector we want is this vector. Okay, that's R2. So negative 0.25, positive 0.433. And so you get positive 0.25 alpha 2, and then negative, did I do that wrong? Yes, I did. This should be negative 0.433 alpha 2, and this one should be negative 0.25 alpha 2. And so then the acceleration of c relative to the origin is negative 0.433 alpha 2, negative 0.25 alpha 2. And then we need to add that to the acceleration of the center of mass relative to the origin. What's that? That's already our, well, this is already one of our variables, right? That's the acceleration of the center of mass. Okay. We're still just getting one side of this equation. And then we're going to set it equal to the one that we already calculated. So this is plus ACOM x and ACOM y. So now we're going to set these two things equal. Negative 0.866 alpha 1, positive 0.5 alpha 1 is equal to negative 0.433 alpha 2, negative 0.25 alpha 2, plus A COM x, A COM y. So that's equations 5 and 6. Any questions about that? Yep.
First acceleration we calculated was the acceleration of c.
According to the first body. Right. And all of this, the stuff after that was calculating the acceleration of c according to member 2. But to do that, we had to use the relative motion equation and the rotation equation.
Is the acceleration of the center mass with respect to the origin also a variable like that?
Yes, it is. Because anytime the reason for that is anytime you don't have a fixed point, your about point is the center of mass, and you have to use Newton's second law, so you need that as a variable. Okay, so 6 equations. We need one more equation. So now require that the acceleration of the point B, y component, is equal to 0. So how can we represent the acceleration of that point B using variables that we already have? Well, we're going to use the same 2 equations. We have the acceleration of B relative to the origin is equal to the acceleration of B relative to the center of mass of body 2 plus the acceleration of the center of mass relative to the origin. And the acceleration of B relative to the center of mass is alpha 2 crossed with R2 plus 0. So the acceleration of B relative to the center of mass, I'll call this R3. So we have 0, 0, alpha 2 crossed with what's this vector? It has to point from the center of mass of body 2 to the point B. So positive 0.25, negative 0.433. So you get 0.433 alpha 2, 0.25 alpha 2, then the acceleration of B relative to the origin is equal to 0.433 alpha 2, 0.25 alpha 2 plus A COM X and Y. Well, that's the acceleration vector at B, but we only want to set the Y component equal to 0. So we have that 0.25 alpha 2 plus A COMY is equal to 0. That's equation 7. And now we have a system we can solve. But I see in my solution I didn't put that 50 Newton force in there, so I'll have to tell you the answer next time. If you have a minute, plug that into your calculator and solve that system before Thursday. So we'll finish this up, and then Thursday we'll spend at least part of the time working on another linkage problem, and then we'll move on to the next stuff, which the next stuff is doing all these calculations in coordinate systems that are accelerating. So you can imagine the chaos that will ensue.